Hello everyone, today we're going to talk about how to make a Huffman encoding. So Huffman encodings are ways to send fewer actual ones and zeros that can encode the same number of bits of information so that we try and compress our data. This is something invented by David Huffman, who was actually an undergraduate here at MIT while he invented it, so it's go make something cool like that, I suppose. So let's say that you have, let's say that you have, erase that, 5 grades that you could get. A, B, C, D, and F. Now they're not all that probable. In 6004, let's say maybe your chances at getting an A are like, let's say 0.3 or something like that. Your chances at getting a B might be 0.2, chances of getting a C 0.15, chances of getting a D 0.15, chances of getting an F 0.2. Probably not that bad, but we can use those numbers for now. So what you do when you want to start making a Huffman encoding is we make these trees like you saw before in lecture, and you can group things together so that we use more ones and zeros to send an encoding for letters which will occur least frequently. So we'll start off with the two least common. So if we take the C and the D here, we'll make them into a new supernode called CD. Oops. CD. Try that again. And the probability of CD is going to be 0.3, right? So we'll do C down here, D right over here. This guy's, 0.15, 0.15, and let's call this a 0, let's call this a 1. It's arbitrary which you pick for either side, and the probability of this guy here is 0.3. So that's going to connect to something else somewhere. So now the next two smallest are going to be B and F. So take these, make them into another node. That's BF. Now, what is probability of BF? 0.4, right? So now we have B and F. So that's going to connect somewhere. So now, what are the two nodes with the smallest probability? Well, we have CD, right? Because we don't have B anymore, we don't have C anymore, we don't have D, we don't have F, remember? So our choices are BF, CD, and A. So looks like A and CD are the two smallest now, so I'll call this ACD, not ACDC, just ACD, and then put A here, probability of that's 0.3, so A connects up here to CD, and the probability of ACD is 0.6. Now we only have two nodes, ACD and BF, and we know that, if we really want to be cute about it, we can, make a supernode called ABCDF, but it looks like we have our Huffman encoding. So if we go back and we say, alright, how do we make an A in this new Huffman encoding of ours? Well, this is a 0, this side's a 1, so it'll be 1, 0. So 1, 0. How do we make a B? 0, 1. How do we make a C? 1, 1, 0. D? 1, 1, 1. And F? 0, 0. So because if we round up, the power of 2, which is closest to 5, is, the ceiling is going to be 8. So we would have to use log base 2 of 8, which is 3 bits for every single letter if we were going to transmit these, to the registrar or something like that. But we're saving bits on A and F because they happen to be the more common grades which might be assigned and sent over to the registrar. And B, sorry. So A, B, and F are all only 2 bits now, so we're going to get some kind of data compression. So if we multiply the frequency with which they occur times, the number of bits that we actually ended up using afterwards, we can come up with our compression ratio. So, show that formula on a new page. Oops. Hang on just a second. There we go. Got our chalkboard back. So we remember A, B, C, D, and F. We had, this one was 2 bits. This one was 2 bits. This one was 2 bits. Or, sorry, C was 3, D was 3, and F was 2, right? So the probabilities, a number of bits, and the probabilities were 0.3, 0.2, 0.15, 0.15, and 0.2. So if we say we have, let's do our formula in a different color. We have 2 bits times 0.3, this is for A, plus 2 bits times 0.2 for B, plus 3 bits times 0.15 for C, plus 3 bits times 0.15 for D, plus 2 bits times 0.2 for F. So once again, this was A, B, C, D, and F. So let's see, how does that work out with math? This gives us 2 times 0.3, so this is 0.6 plus 0.4 plus 0.45 plus 0.45 plus 0.4, which gives us 0.4 plus 0.4 is 0.8, plus 0.6 is 1.4. So this is the average number of bits used to send all of the symbols over, an expected transmission is going to be 2.3. So this is our average number of bits. So we would have had, just to tie it all in together, in the beginning we had no Huffman, we had 3 bits per symbol, right? Now with Huffman we have 2.3 bits.